We already had the form of inclusion and exclusion principle. Now we want to know how to formally prove it. Now let's start proving exclusion and exclusion principle from a simple instance. For example, we want to prove that A complement intersected with A2 complement is equal to the size of universal set minus the size of A1 minus the size of A2 plus the size of intersection of A1 and A2. Now let's prove that for two sets, whether A1 complement intersected with A2 complement is equal to the size of universal set, the size of A1 minus the size of A2 plus the size of their intersection. We give a visual proof here. Let's look at the left-hand side. What does it calculate? It calculates the number of elements that is neither in A1 nor A2. So is the right-hand side doing the same thing? Let's analyze. As the left-hand side is for elements neither in A1 nor A2. For any elements, we need to judge whether it is in A1 or not, whether it's in A2 or not, and whether it contributes to the left-hand side or not. So we could classify the elements. If an element X is neither in A1 nor A2, for the expression in the left-hand side, it contributes 1. For the right-hand side, although it's neither in A1 nor A2, it must be in the universal set. So for S, it contributes 1. But for A1, A2, and the intersection of A1 and A2, its contribution is 0. So the left-hand side is 1, the right-hand side is also 1. For other situations, for example, X is in A1 but not in A2, which means that it's only in one set. Obviously, it won't contribute to left-hand side. For this right-hand side, it must contribute 1 to the universal set. It's in A1, so it also contributes 1 to this set. For A2 and A1 intersected with A2, its contribution is 0. Its contributions to both left-hand side and right-hand side are 0. Among situations such that X belong to A2 but not belong to A1 is very similar. The contribution to the left-hand side is 0. The contribution to the right-hand side is 1 minus 0 minus 1 plus 0 equal to 0. For the fourth situation, which is X is in both A1 and A2. Of course, the contribution to left-hand side is 0. The contributions to every term on the right-hand side, S, A1, A2, and A1 intersect with A2 are 1. So its contribution is 1 minus 1 minus 1 plus 1 equal to 0. By analyzing the four different properties of X, we discover that the left and the right-hand side are equal. So we could prove that we could truly use this inclusion and exclusion principle on A1 complement intersected with A2 complement. Let's try to extend the proof to the situation with M set. Are the sides of A1 complement intersected with A2 complement until AM complement equals to the size of the universal set minus the size of single sets plus the size of intersections of two sets minus the size of intersection of three sets, so on and so forth until minus 1 to the m's power times the intersection of all sets. As was told in inclusion and exclusion principle, the proof is similar to the previous one. Let's look at what it's doing here in left-hand side. The left-hand side calculates the number of elements who is not in any set, which is not in A1, not in A2, not in AM. For an element which is not in any set, its contribution to the left-hand side is 0. In the right-hand side, it isn't in any set except S, as this set contains some A. So for the right-hand side, only S get 1 contribution, or the other set get 0. Both sides get 1. If X is only in one set, it might be in A1, it might be in A2, so forth. But anyway, it's only in one set. So for the left-hand side, it must be 0. For the right-hand side, it's only in one set, it must only appears in one single set AI. For intersections like AI intersected with AJ or AI, AJ, AK intersected, etc., its contribution are 0. So right hand side is 1 minus 1 equal to 0. If it is in 2 sets, 3 sets, so forth, it's in n sets such that n is no larger than m, which means that in the m sets, it's a subset of multiple sets. So the left hand side must be 0. What would the right hand side get? We would think that for S, it's in at least 0 sets among the n set. It's a contribution, so we could use the Cn0 to denote it. For this term, as it's n sets, any set among these n sets would contribution 1 for the right hand side, so it's Cn1. Here all the intersections of any 2 sets among the n sets would contribute, so here is a Cn2. So forth until minus 1 times minus 1 to the m's power times c and m. We are very familiar to this expression. If we complete the remaining terms and add it through minus 1 to the power of n times c and n, we would find that according to the binomial theorem, x plus 1 to the power of m is equal to cm0 times x to the m's power plus cm1 times x to the power of m minus 1 times y, and so on and so forth. Suppose x equal to 1 and y equal to minus 1. We have that cm0 minus cm1 plus until minus 1 to the m's power cmm is equal to 0. So although there are a lot of terms in the right hand side term, the result here is still 0. With this analysis, we discovered that no matter how many sets are x in, the left-hand side is equal to the right-hand side. Both of them are counting the number of elements not in any set. So with this process, we prove the correctness of inclusion-exclusion principle. We just gave a proof for IEP, and actually this theorem has been discovered more than 300 years ago. It's first mentioned in the year of 1718, but it was still a concept at that time. Not until 1854 and 1883 did it appear in the academic papers. At that time, people had judged that although IEP only used simple ideas on inclusion and exclusion, there is a sentence to describe whether it would be useful or not. He said that he thought IEP is actually one of the most useful methods in combinatorics and probability. If you would comment this simple principle very well, you could solve a lot of problems in combinatorics. So for that, next time we will look at this, how elegant IEP should have been.